Hi folks, in this short video I'm going to show you a little bit more about how to evaluate models so that you can get a better sense of doing this in your assignments and in the exam. What we're looking for is a way to deal with models a little bit more efficiently than the standard method that I've shown you so far. So what I'll do is I'll briefly recap that method and then we'll look at a more efficient way of evaluating propositions against models in monadic predicate logic and general predicate logic. Okay, so let's get started. Recall that the basic method for evaluating a model involves looking at how many objects are in the domain, looking at how many variables you have in the relevant proposition that you're dealing with, and then chewing through all of the different possibilities. So to get a sense of how this works, let's just look at a very simple case. Here's a domain of just two objects, and I've got a predicate P, which has one object in the extension, another predicate Q, which has a second object in the extension, and that's the sum total specification of the model. Now if I have a look at a proposition like this, for all x there's some y such that if px then py, I'm going to evaluate that proposition in the sort of long way that I've shown you by looking at all of the possible values that x can take, looking at all the possible values that y can take, and then evaluating each of the conditionals with respect to those possibilities in order to come up with an answer. So what I'm going to do is I'm going to start by putting down the values that x can take. So x can take two values. X can either be 1 or x can be 2. And then I'm going to put down all of the values that y can take. Y can either be 1, y can be 2, and then we take the sentence for all x has some y such that if px then py, and we plug those values through for x and y and evaluate the sentence. So we do that as follows. We set x to be 1 and y to be 1. And this little subscripting notation is just to say, well, for this particular situation, I'm setting x to be 1 and y to be 1, and then I'm going to evaluate the proposition. And when we're looking at these four options, we're looking at all of the possible values that x and y can take. We're looking at all four combinations that there can be based on the number of objects there are in the domain. So the second case, we're saying p1, p2, and this is just saying 1 is inside the extension of p, 2 is inside the extension of p. That's all that little notation is doing. Here, we're saying p2 arrow p1, and then p2 arrow p2. And once we've written down all four of those conditionals, we can evaluate them all based on the truth table for the conditional as follows. Is 1 inside the extension of p? Well, yes, it is, based on the specification of the model, so we can say that that's true. Is 1 inside the extension of p? Yes, it is, so that's true. Based on what we know about the truth table for the conditional, this conditional is true. Next one, 1 is inside the extension of p, 2 is not inside the extension of p, so this conditional is false because the consequent is false when when y equals 2. Here, 2 is not inside the extension of p, 1 is inside the extension of p, so this conditional is true because it's got a false antecedent. And then the last one, false antecedent again, so the conditional is true. So what we see is that the conditional is true for 3 of the 4 possible combinations that we can have for x and y. And now we're trying to work out whether this universally quantified sentence is true, and that universally quantified sentence is universally quantifying over the x and the y with respect, over the x with respect to this existential and the y. So what we're saying is that for all x there's some y such that if x is inside the extension of p, then y is inside the extension of p. And what that means down here is that we need one of these conditionals to be true for every value that x can take. We only need one to be true because this is an existential, and so it's just saying there's at least one case for y where for each value of x, so we've just got to check to make sure we've got one. We look here, we've got one of these conditionals true when x equals 1, so we know that we've got at least one value for y that's going to make this sentence true when x equals 1. We look down here, we see we've got a second value for x where x equals 2, and we've got at least one value for y where this conditional is true, and so we know that it's going to be true for this second value of x, and because it's true for both values of x, this universally quantified sentence comes out to be true, and so this sentence is true given this model. Okay, so that's the long way. What you do is you unpack all of the possible combinations that the variables can take with respect to the objects inside the domain. Then you evaluate your propositions with respect to those combinations in order to come up with some account of whether or not the sentence that you're interested in is true or false. Now, while this sort of way of working out whether or not a sentence is true against a model works for very simple cases, it can become rapidly difficult when you're looking at much more complicated cases. In particular, as you increase the number of objects that there are in the domain, or as you increase the number of variables that there are, or indeed if you do both, you're going to be having to chew through a lot more combinations. In fact, it doesn't take much to make the number of combinations sort of computationally out of reach for most of us. You know, if you have to go through 100 different combinations, that's going to be something that is going to be very inefficient and it's going to be very painful as well. So while this method works for very simple cases, what we really want to do is we want to try and transition from doing it this way in these simple cases to something else when we're looking at more complicated cases. And there's a sort of pragmatic recommendation that I'm going to make, as well as a kind of logical recommendation once we actually look at the more complex cases. The pragmatic recommendation is to do a lot of these kinds of evaluation. So look at a whole bunch of simple models, look at some sentences against those models, and then work out the answers to get a feel for how it is that these sentences interact with the connectives that are in their scope in order to become true or false with respect to a model. Right, so what you're going to use this process for, this simple process for, is to really get a feel of the truth conditions for complex sentences in predicate logic. Then, once you've done that a lot, we're going to move into a second way of thinking about models that is a much more efficient way of evaluating sentences against a model. So let's take a look at that more efficient way now. So let's get a really horrible model, or at least a horribly complex model. So we're going to get a model with a lot of objects in the domain. So here I've got a model with 6 objects in the domain, and I'm going to have a predicate with 3, and then another predicate with 2 in the domain, inside the extension. Okay, so if we have 2 variables and we have 6 different objects, then the number of combinations that we're going to have to chew through if we do it the way that if we evaluate a sentence against a model in the way that we were just looking at is going to be very large. So if we were to look at the same sentence, we'd be looking at a huge number of combinations to crunch in order to work out whether or not this sentence is true. So what we want is some way to evaluate a proposition against a model where we don't have to do that massive crunching of numbers in order to get the result. So the ways to do this, it's not really a sort of process in the same way that the last way of evaluating against a model was a process. Rather, what we do is we look at a sentence and we try and work out what it's saying. And then we use our understanding of the truth conditions of some of the connectives that we're interested in, like the conditional and the biconditional, and we try and evaluate a sentence as quickly as we can based on what we understand that sentence to mean. So instead of looking at the specific details of every value that x can take and every value that y can take with respect to the domain, instead what we do is we sort of take a step back, we look holistically at what the sentence is saying and see whether that sentence is satisfied against the model. So let's have a look at a particular case. Let's look at an easy case first. So consider this sentence. For all x, px. Now, one way that we could evaluate this model is to look at every value of x that x can take in the model. So there's 6 different values, and then look and see if all of those things are inside the extension of p, right? Now, that wouldn't be too bad in this case, but imagine that your domain had 10,000 objects in it. You would have to go through and check every single one in order to work out whether or not this sentence is true. Doing it the hard way would be really difficult in this case. A better thing to do would be to look at that sentence, work out what it's saying, and then see if the model satisfies that sentence. So what's this sentence saying? Well, it's saying that everything is inside the extension of P. Everything has that property. So everything inside the domain has to be inside the extension of P in order for this to be true. So I don't need to go through all of the possible combinations for X that the domain can, that X can take from the domain in order to see that this is false. Because all I need in order to see that this is false is that there's something inside the domain that is not inside the extension of P. So I know immediately that this case is false. All right, and so what I did is I just looked at what the sentence was saying, looked at the relationship between the extension of the predicate and the domain, and saw that the predicate wasn't, that the sentence wasn't satisfied given the extension for the predicate and given this specification of the domain. All right, so that's a very simple case. But when we're doing more complex cases, we sort of just keep doing the same thing. So have a look at this case. For all x, there's some value for y such that px and qy. Right? So now what is this sentence saying? This sentence says, for all x, it's inside the extension of p, and there's some y that's inside the extension of q. Right? So again, we could go through the possible combinations for x and y, we could chew through all of those combinations. In this case, we would have 6 combinations for x, and then for each of those combinations for x, 6 combinations for y. We'd be looking at a large number of combinations to chew through. But again, it's not really necessary. What we can do instead is just look at the sentence and see that the conjunction here is false because the universal claim is false, right? So the universal claim is saying that everything is inside the extension of P. We already know that it's not the case that everything is inside the extension of P, and so we know that this universal claim with respect to this conjunction is false, and that's enough to know, based on our understanding of the truth conditions for the conjunction, to know that this entire sentence is false. All right, in other words, this is saying that everything is inside P and something is inside Q. That sentence is false because it's not the case that everything is inside P. And we didn't have to go through all of the combinations to work that out. All right, another case. Let's look at one with a conditional in it. So imagine this, for all x, if px, then there's some y such that qy, okay? So in this case, if we were to evaluate this sentence in the sort of detailed way that I did at the start of this little video, we would look at all the values for x and all the values for y and go through the full roster of combinations. Instead, what we're going to do is we're going to do 2 things. First of all, we're going to notice that when we're dealing with this universal and we've got a p, that predicate inside the scope of the universal, what this whole sentence is saying, for all things, if they're inside the extension of P, then something else, right? So immediately, we only need to be concerned about the things that are inside the extension of P. Anything that's outside the extension of P is going to go false for that antecedent of that conditional, which is going to make the conditional true. So we don't need to worry about those cases. We know that the conditional is true in those situations. What we're really interested in is it true in the situations where something is inside the extension of P, like where we're looking at one of the things, that's inside the extension of P. So what we're looking at are just 3 cases. We're just looking at this 10, 20, and 30 case. And now what we're looking for, we look at the right-hand side of this conditional, and what we see is that it's saying that there's something inside the extension of Q. So what this is saying is that for all things, if they're inside the extension of P, then there's something inside the extension of Q. All we need to make this bit here true is for there to be something inside the extension of Q. And indeed there is. Right? So we know that there's always going to be something that we can put in for y that would make the right-hand side of that conditional true. So no matter what value for x we put in, whether it's 10, 20, or 30, we know there's always something for y that we can put in that's going to make the conditional true. In other words, there's nothing I can put in here for x and y that is going to falsify the conditional, and so we know that that conditional is always going to be true, which makes the universal claim right out the front true. So what we're doing in this holistic method is we're really just trying to work out what these sentences say and see whether or not the model in question actually makes a sentence true. That's sort of one way of looking at this holistic method. The other way of looking at this holistic method is to take a sentence like that and see if you can make it false. Try and counterexample it using the model that you've got. So let's have a look at this sort of slightly different way of evaluating sentences against models and in order to see how it works. So we're going to keep with the same model. Just going to get rid of this sentence. We're going to look at a slightly different sentence. We're going to look at something like, for all x, if px, then not, if px, then qx. There we go. All right, so for all x, if px, then qx. Now, how do we work out whether this sentence is true? Well, let's take a look at what the sentence is saying. It's saying, for all things, if they're inside the extension of P, then they're inside the extension of Q, right? So suppose that we had two properties being round and being red. A sentence like this might say something like, everything that is red is round, okay? That's not what's happening in this model because we're dealing with numbers rather than colors, but I'm just trying to get you to see the basic idea that what this sentence is doing is expressing a relationship between these two properties. Once we understand that the sentence is expressing a relationship between these two properties, we can look at the model to see if the relationship is satisfied. What we're going to be looking for in particular is there something that is it the case that everything inside P is also inside the extension of Q? For all things, if they're in P, then they're inside the extension of Q. What we're going to do is we're going to try and make this sentence false. We're going to try and counter-example it by finding something that's inside the extension of Q that's not inside the extension of P. And if we look at the model, we can do that pretty easily. So we look here, we see that 60 is inside the extension of Q, 60 is not inside the extension of P, and so we know straight away that there's some value we can put in for x that would make the left-hand side of that conditional true and the right-hand side false. In particular, if x equals 60, sorry, I've done this around the wrong way. What I meant to say was that what we're looking for is something that's inside P that's not inside Q. What I did was identify something that's inside Q that's not inside P. So we need to actually look at the slightly reverse case. So let's look for something inside P that is not inside the extension of Q. If we look for something that's inside P that's not inside the extension of Q, we can have a look and see immediately that 20 is inside P that's not inside the extension, and it's not inside the extension of Q. So if we put 20 in for x, if we say that x equals 20, then we know that P 20 will be true, Q 20, which is to say 20 is inside the extension of P, that's true. 20 is inside the extension of Q, that's false, which makes this conditional false. And all it takes to make this universal claim false is one instance that makes the conditional false. And we've got that immediately by seeing that there's something we can put in for x, namely 20, which will make the left-hand side of the conditional true and the right-hand side of the conditional false. In general, when you're trying to work out whether or not a sentence is true and it's a universal sentence, it's often quite good to try and see if you can make that sentence false given the tools that you've got available to you. So if you look at the model and you can see that there's some way of making the conditional or whatever it is that's inside the scope of the universal false, then you know there's going to be some instance that will make the universal false, and that's going to falsify the universal with respect to this particular model. If you're looking at an existential, the sort of opposite is true. What you want to do is you want to try and make that existential true because you only need to find one case in order to do that. And so if we sort of take a step back and think about what we're doing from a kind of efficiency perspective, what we're doing is rather than chewing through all the possible combinations, we're trying to zero in on a particular combination that's going to get us the answer really quickly. So with respect to a universal, we try and find the falsifying case because if there's just one of those, then the whole thing gets to be false. Similarly with the existential, we try and find the case that makes it true because if there's just one of those, then that's going to make the whole thing true. So when you're trying to evaluate against these models, take a step back, work out what the sentence is trying to say, and then evaluate the sentence rather than looking through all the possible combinations. Chewing through the combinations will help you to understand what these sentences are saying, but ultimately you'll need to step away from that and do this more general thing. Let's look at a case in general predicate logic as well. So let's start with the new model. This model we're going to put 8 things inside the domain. We're going to have a 2-place predicate. And we're going to have a 1-place predicate. Like that. And now we're going to take a sentence in general predicate logic and we're going to evaluate it against this model. So for all x and for all y, if ax y, then bx. Okay? So there's a relatively complex proposition. Again, if we were to do this the long way, we'd have to look at 8 values for x, and then for each one of those 8 values for y, which is going to make the space of combinations that we've got to chew through quite large indeed. Instead, let's have a look at this sentence and see what it's trying to say. What the sentence is saying is that for all things x and y, for any ordered pair that you can think of that sits inside the extension of A, the first term in that ordered pair, whatever the x value is, that thing is inside the extension of B. So for all of the things that satisfy this left-hand side of the conditional, the x things that do the satisfying are also inside the extension of B. Which is to say that for any of the ordered pairs here that are inside the extension of A, the first term has to also be inside the extension of B. So for instance, you would need it to be the case that the 1 in this ordered pair here is inside the extension of B, and the 3 in this ordered pair here is inside the extension of B. So already we can see that the sentence is false. The sentence is false because it's not the case that every value that we can put in for x and y here is such that the x's will be inside the extension of this B predicate here. And what we can do is we can zero in on this answer by trying to counter-example it, by trying to find the falsifying example. And the falsifying example comes by looking at this, this extension here and seeing that there's something in the first term here that doesn't appear in this set of objects inside the extension of B. So we can find that counterexample, x equals 1, and y equals whatever you want. Actually doesn't matter all that much so long as y is the second term in one of these ordered pairs. So let's set y equals 2. And if we plug that into this conditional, we're going to get A, 1, 2, like that, arrow B, 1. And we know that 1, 2 is inside the extension of A, so that's going to be true. But 1 is not inside the extension of B, so that's going to be false. So this conditional is going to be false. And all it takes is one instance of this conditional to falsify this entire double universally quantified sentence. And so we know that this double universally quantified sentence is false. And of course, this sort of under-the-hood procedure that I spelled out here is not entirely necessary for seeing that this sentence is false, because we can see that for all things x and y, if they're inside the extension of A, then they're inside the extension of B, the x things are inside the extension of B is false, because there are ordered pairs here where the first term doesn't appear in B at all. So with respect to models, whether you're looking at monadic predicate logic or general predicate logic, rather than trying to chew through all the combinations, what you can do is try to work out what the sentence is saying. What relationship is it specifying between the things inside the model? Is it saying that the things inside A are inside B? Is it saying the things inside B are inside A? Is it saying that every one of the things that is in a particular state inside A is inside B? Is it saying that things are inside A only if they're inside B, and they're inside B only if they're inside A, and so on? You look at those relationships, and those relationships are really given to you by the way that this connective interacts with the quantifiers, and then you use those relationships in order to try and evaluate the sentence with respect to the model. And that's going to save you a lot of grief. It's going to save you a lot of time chewing through these combinations. Instead of chewing through those combinations, you just try and work out what the sentence is saying and see if the meaning of the sentence is in fact satisfied by the model that you're interested in. Okay, so that wraps up this sort of second way of approaching these models. Just to summarize the basic idea, you've got one way of doing models, evaluating sentences against models, where you look at all of the possible combinations and you chew through those. That can be quite cumbersome. The other way of evaluating against a model is to look at the sentence, work out what it means, and then see if those conditions that the meaning gives you are satisfied by the model itself. And you can use that more holistic approach with monadic predicate logic, with general predicate logic. Ultimately, you really need to practice with these models in order to get a sense of that holistic approach. You need to get a lot of experience with understanding what these universally quantified sentences are saying, drawing out the meaning, working out what would make them true or false, before you can get sort of really efficient at evaluating these sentences against the model. But it can be done. You really need to just practice with respect to these universally quantified sentences. Okay, thanks for listening and good luck with doing models in your assignments.